Now in terms A and B, we aren't actually even looking at the separation mechanism itself or how the analyte is interacting with the mobile phase or with the stationary phase. We're just looking at what's going on because of the underlying movement of the particle or the analyte through a series of particles, or how it's simply diffusing over time because of concentration. Now, the next term, term C, is broken into two parts. Term C overall is called a mass transfer term, but we can look at how this affects the mobile phase and for the stationary phase. So we break this into two parts, term Cm, which is mass transfer in the mobile phase, and in the next video we'll look at term Cs, which is mass transfer in the stationary phase. So for mass transfer in the mobile phase, what we're going to do is we're going to first consider that we have, let's say, an open tubular column, okay, and I'm just going to draw on its side this time here. So remember, open tubular has the stationary phase all along the surface, okay. Here's my stationary phase. This is open tubular. And then I'm going to take my, use a red pen for this. I'm going to take my little analyte. Here's my analyte. Okay, this analyte just got done interacting with the stationary phase on that side of the column, and it's going to return to move across the column. Now let's assume that there is no movement of the mobile phase just for this first scenario. So without any mobile phase movement, the most direct path it can take is to go straight down to the stationary phase on the other side. Okay, so the most direct path is to go straight from the top to the bottom. Now let's assume that we have the mobile phase flowing. So this is no flow here. What happens when it's flowing? If it's flowing at a very low rate, as it starts moving down, it's going to move at an angle because the flow rate is going to, the flow of the mobile phase is going to start pushing it over. Okay, so this is a kind of a low flow rate. Now what happens if we've got a very high flow rate? Okay, now the high flow rate is going to push it really far. Okay, so this is going to affect the way in which this analyte can move between one stationary phase part on the column and another one. It's going to be affected by that. So we know then that this effect is that as we move through the column here, that if it's moving at a high flow rate, what we ultimately have is less interactions with the stationary phase, right? If it's only moving a little bit and then it comes back out and it now kind of zigzags, we'll do a second line here. And comes up there, and comes down here, and comes up there. If that's the order that it's taking, it gets several interactions with the stationary phase. And we know that it's the interaction between the analytes and the stationary phase that ultimately leads to separation. So we want as many interactions as possible to get high separation. Remember, this comes back to the idea that we're doing a series of mini extractions every time the analyte encounters the stationary phase, and the more small volume extractions we do, the better the separation efficiency we get. So in this case, we get several, but if our flow rate is really high, now we get very few interactions in the same amount of column. So we're going to get a lower efficiency of separation simply because we're not encountering the stationary phase as well. Okay, so in this case, what we have for Cm is when we write this out, we get Cm is going to, or the mass transfer in the mobile phase is going to be directly proportional to the flow rate. Okay, so again, we've got flow rate here and our Cm, mass transfer in the mobile phase term. Okay, so if we're trying to determine how we can minimize this, we need to know what components make up Cm. And what we'll find is there's some function of retention factor, and this function of retention factor, we know that the retention factor is analyte specific, and it basically relates the affinity for the mobile phase to Cm. Okay, so the more time it spends in Cm, the more affinity it has for it, the more of an effect this is going to ultimately have, because the analyte is spending more time in the mobile phase. So it can be moved at a greater effect. Now, the other thing that this takes into account is the radius of the column. And this is for an open tubular column that we have the radius of the column. Now, if you have a packed column, we would use the particle diameter instead, okay? So for a packed column, where we have r squared would instead be dp squared. Okay. Now, why is this important? Well, if we have a narrow column, then the analyte is the difference between moving at a high flow rate and a low flow rate is not going to lead to as many different or so as big of a difference in the number of interactions it gets with the stationary phase, because it simply doesn't have as far for that angle that we're creating based on the flow rate to make as big of a difference. Okay, so a smaller radius is going to limit the Cm term. Additionally, smaller particle diameters for a packed column mean that that column is going to be packed more tightly. You can think of this as putting big rocks into a beaker versus grains of sand. The grains of sand are going to be able to pack more closely to each other, and so there's not as big of a space where mobile phase fills for the analyte to have to traverse from one particle to another. So in this case, when we start looking at these function of retention time and the radius, we're really concerned with how much time is it going to spend in the mobile phase. The other thing that we need to include is a diffusion factor. Now, if an analyte diffuses very quickly, it's going to be able to traverse this very, very quickly. And the faster it can traverse this, the less effect the mobile phase flow has, because the less time it spends in the mobile phase, the less the mobile phase is going to be able to push it. So a fast diffusion rate is going to ultimately lead to a smaller overall Cm term. Now, if this analyte is moving very slowly through the mobile phase with a very low diffusion in the mobile phase, this is our diffusion factor, then we are ultimately going to spend a lot longer in the mobile phase than we otherwise would, and that's going to make the Cm term large. So diffusion in the mobile phase here. All right, so some of our main takeaway points here. Mass transfer in the mobile phase is all about getting that analyte to move through the mobile phase from stationary phase to stationary phase as quickly as possible, because the flow rate is going to be pushing it along to make it have fewer opportunities for stationary phase interaction, which ultimately leads to good separation. So here's the areas that affect it. We have the retention factor, so the affinity of the analyte for the mobile phase plays a role. We also know that the radius of the column or the particle diameter, depending on if you've got an open tubular column or a packed column, is going to play a role, as well as the diffusion in the mobile phase.